Okay, so today we're going to finish off talking about the discovery cycle, and then next week we'll move on to credibility. We were talking last time about this problem, the problem of noticing. And last time we talked about a couple of examples where the problem of noticing is pretty trivial. The problem is not actually a problem. The discovery of Viagra, the discovery of LSD, those were things where the phenomena of interest imposes itself with considerable force on people, but there are lots of cases where it's not so trivial. And it's especially not trivial when you've got something very specific that you're looking for. And Grinnell's trying to convince us that very often that's having a very narrow focus. While it's productive if you are focused on the right things, it's not always going to be the case that you are focused on the right things. Very often there's going to be something just outside of your field of view, just outside of the things that you're looking for that is important and interesting, worth studying, and that then noticing becomes a problem in the sense of a challenge. Not that it's problematic, but it's that it's a challenge that scientists have to kind of grapple with. We talked a little bit about Plato's paradox of discovery. Turns out not to be really a paradox, but he presents it as one. So a man cannot search for either what he knows or for what he does not know. He cannot search for what he knows since he knows it. There's no need to search, nor for what he does not know, for he does not know what to look for. This is just the idea that Plato's arguing that he's literally arguing that you can't actually learn anything. Somebody came up to me after class and very sensibly asked what he could possibly be on about here, because of course he was a teacher, he was a student, of course there appears to be learning happening. I forgot to say what his actual solution was. So Plato's got this very weird epistemology, weird from our perspective, where learning is actually remembering. So he thinks that all of the important facts about the world, the sort of timeless, eternal facts, are things that before you were born, your soul existed and it sort of lived amongst the forms, and you knew all of the really important stuff, and then you just forget it when you're born. And then as you're learning things, important stuff like mathematics, what you're really doing is remembering. And his proof for this was to, via a series of leading questions, get a child who had no training in mathematics to sort of come up with mathematical proof. So by showing that you could draw mathematical knowledge out of somebody who had no training in mathematics, he was showing that really you're just remembering all of this stuff. I take it that most of us don't subscribe to that sort of epistemology. We actually think that we learn things. But nonetheless, there is this sort of active question about how that could be the case. So in the problem of noticing, there's this problem of like, how do you notice something that you're not looking for? Since, how does something that you're not looking for grab your attention? How does it come into your consciousness or something like that? And scientifically, we might ask, so how does something outside of our scientific framework enter into the scientific framework? Because your evidence is evaluated from within a framework, right? Your claims are framework bound. We've talked a little bit about the theory-ladenness of data. So your data is interpreted through some paradigm or other. So how is it that we sort of shift from one paradigm to another? Or how is it that you come up with anomalies within a paradigm, that kind of thing? So I tried to develop this example. I mean, this is, for my money, the nicest example of this, where, I mean, you resolve the paradox of, Plato's paradox by not, when you learn something new, you don't learn it all at once, right? So we're currently learning stuff about the cosmos. We're learning, for example, we've observed a bunch of galaxies, and we have very good models of how they should behave given how much we can measure the mass, the visible mass of the galaxy, and build a model of how it should move over time. And the models and the predictions and the observations don't match up at all. They're very, very off. So we've constructed this kind of label for our ignorance. We put a name on this anomaly. We called it first dark matter to explain the kind of gravitational anomalies. These galaxies behave as though they're way heavier than they actually are. And then dark energy is meant to explain the fact that it looks like the expansion of the universe is accelerating, which I mean, weird. It's very weird to see. I mean, there's nothing visible that we can actually see that would explain why the expansion of the universe is accelerating. So we stuck a label on our ignorance. We called it dark energy. So we're getting some, I mean, we're making a lot more progress on dark matter than dark energy. The dark matter thing, we're actually now we're at the point where we can make maps of it. So you can actually sort of map out where it looks like there's more matter than we can actually see. Actually, we're come all the way back around. So this is a kind of anomaly. We stuck a name on the anomaly, and now we're able to study it. So we're able to quantify it, we're able to map where it is, and we're able to learn about it. And hopefully by doing that quantification and those maps, we'll be able to figure out what it actually is. We're not at the point right now where we know what dark matter is. There's a bunch of theories, none of them are confirmed. Actually, now they're starting to turn up anomalies within this way of talking about the anomaly. So we're finding galaxies that look like they don't have any dark matter in them. And that's sort of a double, it's an anomaly within the anomaly. They're behaving as though the model works, and that's weird in itself. So the point here is just, so thinking about the Plato's paradox of discovery, Plato was speaking as though you have to either completely know what you're talking about or not know what you're talking about. And if you completely have no idea what you're looking for, then maybe you can't see it. You can't kind of begin to learn about it. But that doesn't look like how learning actually works. We learn by degrees. We first discover that something's not quite right, and we can say, that's not quite right. And then we can stick a label on that phenomena, dark matter, dark energy, and then we can start the learning process about those things. We can actually formulate a concept for it and say, this weird thing is happening, now let's try to study it. Let's try to learn more about it. And that's a kind of incremental process of learning rather than all or nothing. So Plato generates this apparent paradox by pretending that learning is an all or nothing, completely on or off sort of affair. And the resolution, Grinnell thinks, is more or less just to say, it's not all or nothing, it's a by degrees sort of thing. Okay, so we've been talking a fair bit about paradigms. We're going to keep talking about paradigms because these are part of the solution to the problem of noticing. The problem of noticing, I mean, the real problem is that there's just way too much available to notice. At every moment, we've got way more possibilities for things we could observe than we could possibly observe. We've got way more experiments than we could run than we could possibly run. Like in the sense of there's way more like out there that could be run, and there's way more ways of analyzing data from an experiment than we could possibly analyze. So a paradigm is a kind of way of narrowing those possibilities down. Say these are the important ways of making observations, these are the important experiments to run, these are the important ways of analyzing the data once you've run the experiment. So a paradigm narrows your view. It excludes almost everything. And you want that. You want that because the possibility space is just vast beyond comprehension, and you need some way of navigating it. And a paradigm is a way, scientists get into a paradigm when they find a way of narrowing the field down that's productive. And they use paradigm is a set of common language and assumptions and beliefs and methods, examples and all this stuff. Typically undergrads get sort of inculcated in this stuff when you start learning a science. So they teach you the paradigmatic examples and methods and the vocabulary and all the stuff that sort of constitutes a paradigm. And that's a temporary solution to this problem of noticing. But it's only ever a temporary solution, or at least until we're finished. Maybe someday we'll just completely finish science and we'll just know all of the important things there are to know. I don't know, I mean, keep going for 1 billion years, maybe we'll get there. But so far in the history of science, we've only ever seen these as temporary solutions to the problem of noticing. You say, these for now are the most promising experiments to run, these for now are the most promising observations to make, and so on. And it's extremely helpful, and it's got its limitations, of course, because once you're in a paradigm, it's hard to see outside of it. Okay? So we didn't quite get to this last time, but some examples, some prominent examples of paradigms. I think I've talked about this one already, sort of Newtonian mechanics. If you did high school physics, this is what you did. This is the kind of mechanics or physics that typically engineers will use. So for medium-sized, slow-moving dry goods, Newtonian mechanics is really good still. And it makes some really substantial assumptions about the nature of reality. So here's one that's utterly uncontroversial to us, but was controversial, during the scientific revolution. Basically, that nature can be described mathematically. For Aristotle, this was absurd. So nature itself couldn't be described mathematically. Mathematics describes the kind of form of reality that our natural world only ever imperfectly matches. So the idea that you would use math to do physics was something that Aristotle would have rejected. So his physics had no math in it. Whereas, of course, by the time you get to somebody like Galileo and Newton, they're using mathematics to describe the world. So it's a substantial assumption. It's an assumption that took quite a while to kind of develop. Mathematics was used for things like geometry literally translates to the geo-earth metry, measure of the earth. So you would certainly use geometry to do things like figure out how big your plot of land is or something like that. But that was considered a kind of imperfect, there's no perfect circle, there's no perfect square. So mathematics applies only imperfectly to the messy world that we inhabit for Aristotle. The idea that you would use it to kind of get at the deep structure of reality was a substantial philosophical and paradigmatic shift. So that's an assumption that Newton picks up that we kind of carry on till today. Here's one that Newton held that we gave up on. So space and time stay the same and objects move around. So that's, there are absolute points in space. Yeah, that space is sort of absolute. It doesn't change, but objects do move around in space. And that's, in relativity theory, that turns out to be one of the fundamental assumptions that we have to reject. So in relativity, we only talk about the relative position of things. And space itself changes as massive objects move through it. Space and time are warped and distorted by physical objects. For Newton, space is just totally static, empty, it's absolute. There's a fact of the matter about where objects are. And for Einstein, space is only ever relative. So you can picture the difference, the conceptual difference here. There was a debate between, I believe, Newton and Leibniz about the relative or absolute nature of space. Imagine a completely empty universe, except for a bucket of water. Yeah? So if space is absolute, then if you spin that bucket of water around, the water should rise up the sides. Yeah? But if space is relative, and the bucket is the only thing in there, then it makes no sense to talk about the bucket spinning. There's nothing for it to be spinning relative to. So for Newton, it makes perfect sense to imagine a completely empty universe, bucket of water spinning around, because space is staying still and the bucket is spinning. But if space is only ever the relative position of objects, completely empty universe, there's no, the water doesn't rise up. It's just sitting there because there's nothing for it to spin relative to. So Newton lost this debate. As far as we can tell, space is relative. So this is an assumption built into the mathematics of Newtonian mechanics that works very well for a couple centuries, still works for most practical applications, but we have to give it up when we move to relativity theory. And another quite substantial assumption, the forces acting on objects can be added and subtracted. So things add up linearly. The forces acting on an object add linearly. Yeah? Again, this is it's a deep assumption of the model, and it turns out to be extremely useful. I don't know, does this remain in quantum mechanics? Like quantum mechanics and Einsteinian relativity are both nonlinear theories, highly nonlinear theories. So the linear additivity of forces doesn't necessarily hold. Anyway, so These are the deep assumptions underlying Newtonian mechanics. They're things that you, in some sense, see through. You don't even look at them as claims. You see the world through these assumptions. And some of them get added in around the time of Newton or a few centuries before. Some of them Newton holds on to and we have to reject later. So these are the assumptions that sort of constitute a paradigm. They kind of have to shift over time. Here's another one we haven't talked about as much, behaviorism. So this is a movement in psychology in the mid-20th century. So mid-20th century, we don't have EEG machines, we don't have fMRI machines. Our knowledge of the brain is mostly from dissecting cadavers and horrible accidents. Those basically are access to how brains work. So really so here's a deep assumption about science. Science needs to be about things that are publicly observable. The behaviorists were reacting against what's called the introspectionist movement in psychology, where people would try to use people's subjective reports of their own experience as data. Say, okay, now tell me what you're seeing, tell me what you're feeling, tell me how that tell me about your inner world. And the behaviorists found this to be scientifically suspect because you're the only person that has access to your inner world, whereas science is supposed to be about publicly observable, publicly verifiable facts. So what's the only part of psychology that's publicly observable, that's publicly verifiable? Of course, it's your behavior. It's your behavior in response to the situations that you find yourself in, this relationship between stimulus and response. So kind of for these deep scientific scruples and because of the state of technology at the time. Now, of course, now we don't think that that's the only part of psychology that can be publicly observable because we can look inside the living brain of a human being and see what it's doing while we're doing stuff. So you can strap somebody up with an EEG machine and watch how their brainwaves change. You can put them in an fMRI machine and see how their blood flow is changing as they're doing various things. So we have much better access to what we call the inner processes of psychology. So we're able to connect up people's behavior with what's going on in their bodies and their brains. But at the time, the only thing that was publicly observable was stimulus and response. So they talked about inner processes being black boxed. That is, they're treated just as not part of the theory. Yeah? So the scientific theory of psychology during the behaviorist era was entirely about functions that would relate stimuli to responses. Yeah? So the idea was that you could reconstruct all of the complicated things that people do in terms of simple reflexes, simple conditioned responses, kind of chained together in elaborate ways. So obviously human beings behave in complex ways, but the hope was that all of those complexities would eventually be reducible down to simple stimulus responses. Yeah? Conditioned by reward and punishment. So this is a set of beliefs about what counts as good psychology. You know, what is a good method in psychology, and specifically rejecting the method of introspection, asking people about what their inner states are like, and focusing on behavior in response to stimuli. So the kind of experiments you can do are experiments where you present a stimuli and see what they do, and then you try to mathematically model the relationship between the stimulus and the response. So that's what counts as an observation, what counts as an experiment, and what counts as a theory. A theory is a model of the relationship between stimulus and responses. Now, so this was a very serious paradigm in psychology for a long time. Okay, so within that era, have you heard of rat park before? Anybody here heard of rat park experiments? Oh, I'm very excited then. Very good. Okay, I'm glad that none of you have heard of this. I always like telling people new stuff. Okay, so within this behaviorist paradigm, there was a set of beliefs about addictions. And the behaviorist paradigm involved, I'm sorry to say, a whole lot of animal experiments. So they tortured a lot of rats. They really did a number on a whole lot of rats and cats and dogs and primates. It was bad. And when we're trying to understand drug addiction, here's where a huge amount of the data came from, the type of experiments they would run. So what you want to do is get a nice clean signal on the relationship between a stimulus and a response, right? So what you want to do is have the simplest possible environment, stripped of all the complexity, and just have only the stimulus, and then you observe the response. So you want to understand, for example, the action of morphine or heroin on a mammal. So you want to understand what this does to a mammal. So what you do, you put a rat in a bare metal cage, just that rat, one rat in one cage, and you give it 2 water bottles, one pure water and one water laced with morphine. And what they found was almost all of the rats would drink the morphine-laced water basically until they died. They would just dose and dose and dose until they overdosed and died. And the conclusion here was, if you give a mammal access to morphine, they will become horribly addicted, they will become deeply, deeply dependent, and they will keep using it until they die. That's the conclusion that they came to. So this fits very nicely within the behaviorist paradigm. You want a nice, clean, you eliminate everything but the stimulus, and you watch the response. And they found that rats who are addicted to morphine would do practically anything to get more morphine. So if you make them go through some unpleasant task to get more morphine, they absolutely would. If you took the morphine away, they become very upset, that kind of thing. So what's not considered relevant here is things like the environment that the rats are in. And there was, in the 1970s, a psychology researcher in Canada, actually in Vancouver, called Bruce Alexander, who started wondering whether this was an adequate measure of the kind of things that mammals do in response to drugs like morphine. So Bruce Alexander created what he called Rat Park. So the fact is that rats are highly social. They like hiding, they like exploring, they like hanging out with other rats. And so he built this kind of communal situation for a whole bunch of rats. They would live together, they could run around, they could play. There was kind of enhanced environment, little tiny trees. I don't know. It was cute. He was cute about it. But I think the most important part, I suspect, and this was Alexander's conclusion, is that they were allowed to socially interact. Rats are social animals, and he provided them again water that was just pure water and water laced with morphine, and the rats would have a little morphine. It's not like they had none. But they did not do the thing that a rat in a bare steel cage would do, which was just dose and dose and dose until they died. Some rats would have none of the morphine, some liked it a little more, but mostly they would do not so much that it would impair their ability to interact socially. So when given the opportunity to have a social life, rats would choose a social life over morphine. If you took a rat, got it horribly addicted to morphine in one of these steel cages, and put it in Rat Park, it would fairly quickly put itself through rehab. It would fairly quickly become unaddicted and choose to live a normal rat life over just going wild on morphine. And I don't know about you, if I was locked in a tiny steel cage with nothing to do but morphine, I would do a buttload of morphine. I would go wild on that stuff. I would get into deep trouble because literally nothing, they had nothing else to do. Their only behavioral options were drink regular water or get high on morphine. I would do a lot of morphine in that situation. I would. I think it's hard to blame them given the circumstances that they were in. So what comes out of this is a different way of thinking about addiction, that maybe addiction has less to do with the intrinsic properties of the chemical and more to do with trying to cope with an intolerable life. So, and when you look at patterns of addictions in humans, it's almost inevitably humans who have lives that are for one reason or another intolerable, from just having, all of the variety of things that can make life intolerable. If you have an otherwise pretty decent life, it's actually very hard to get horribly addicted to drugs, which is not to say that drugs don't have like withdrawal symptoms if you stop taking them. So like morphine or benzodiazepines have horrible, or SSRIs have very substantial withdrawal symptoms if you just immediately stop using them. But it doesn't seem to be that people with an otherwise perfectly nice life will become immediately hooked on drugs, even if they have them freely available. So when we're thinking about paradigms of research, what we're thinking about is what gets included as relevant as part of the test and what gets counted as irrelevant. Yeah? So back to the problem of noticing, back to the question of paradigms as solutions to the problem of noticing. For the behaviorists, the kind of having a social animal like a rat, being allowed to have a rich social life was not regarded as relevant to assessing the relationship between stimulus and response. Yeah? That wasn't within the paradigm. Yeah? That wasn't part of what was being tested. And these are fairly controversial studies. Like to this day, these are controversial studies. There have been attempts at replication that didn't go as well as Bruce Alexander's, but I think it's really interesting to think about the different ways in which researchers treat aspects of the situation that you're testing as relevant or irrelevant. Yeah? Alexander's work seemed to show that it was less the morphine and more the bare metal cage that was relevant to these rats. Like almost 100% of them would, in the bare metal cage, would dose themselves to death. And almost none of them in Rat Park would do that. Okay? They'd have a little morphine as a treat. Okay, so, yeah, so basically it's what is good about a paradigm is that it tells you what's important. What's helpful about a paradigm is that it divides the world into relevant and irrelevant. What's dangerous about a paradigm is that it divides the world into relevant and irrelevant, right? It divides the world into things that are worth thinking about and things that aren't worth thinking about. And the fact is that the chances that you got that cleanly and correctly decided right off the hop are very low. Yeah? It's very, very unlikely that in the extremely messy and complicated universe that we're exploring, we're just going to get it right straight off the bat. We know what's important. We know what's worth testing. So it's both the strength and the weakness of paradigms. Yeah. So that was the Rat Park experiment. So it's not just, so it is a perceptual problem in the sense of knowing where to put your attention. It's also a question of deciding which hypotheses are worth testing and how hard. So in the behaviorist paradigm, the hypothesis that environment would greatly mitigate the effect of morphine on rats simply wasn't worth testing. That wasn't worth spending the money to set up an elaborate, rat park. But as it turns out, that was at least an interesting and important hypothesis to consider. So paradigms can help us to set up our questions, set up our hypotheses, direct us towards worthwhile hypotheses, but they can also, in some important sense, blind us to those questions that might be worth asking, but are hanging around just outside of our paradigm. This is, again, this is why I really like the binocular metaphor, because binoculars, really powerful enhancers for your vision, of course, but they greatly reduce the scope of your vision. You just get a little restricted tunnel. Yeah? Okay. So I want to propose to you that this is not just a thing in science. Actually, this is a very general feature of cognition, very general feature of thinking and reasoning, that when we go to solve a problem, we bring assumptions to bear on that problem. And often, they're just the wrong assumptions. Often, the way that we've framed a problem will make it impossible to solve it. And what we need to do, we might call those type of problems insight problems. If you're in an insight problem, the thing that you have to do is, in some sense, break out of the way that you framed the problem and reframe it. In the scientific context, that would be something like a paradigm shift. So that's something like what Alexander did. He says, okay, I'm gonna question the very assumptions of the paradigm that I'm in, try to reformulate those assumptions, and do something different. Hard to get funding for that, but it's often worth doing. So, many problems in our lives are not like this. Many problems in our lives are fairly straightforward. The assumptions that you bring to bear are perfectly good. If I want to multiply 7 times 7, I don't need to do any complex reframing, breaking out of my assumptions, anything like that, of course. But sometimes, actually fairly often, you do have to do this stuff. So this is a classic insight problem that they use in psychology research. It's called the 9-dot problem. 9-dot problem. So the problem is this. Draw 4 continuous straight lines through these 9 dots. Yeah, that's it. That's the whole problem. Just draw 4 lines without lifting your pen. Draw 4 lines that cover all 9 dots. And you go 1, 2, 3. Oh, that doesn't work. 1, 2, 3. Oh, that doesn't work. I'll do this on the board. Okay. Has anybody seen this before? A couple of you? Okay, so none of you are allowed to answer this thing. What do you think?
About what?
Well, what's the answer to the problem?
What's the problem?
Connect all 9 dots with 4 straight lines.
Oh, right. How big are the lines?
Big as you want them. They've just got to be straight. And each line has to start from the end of the last line. Okay. So in psychology tests, the spontaneous solution rate to this, the unassisted solution rate to this problem is approximately 0. That is, almost nobody gets it. Let me show you the answer. Let me see if I can remember the answer. Oh God, oh God. Here we go. Right. Oh God. Yeah, okay. 1, 2, 3, 4. And when you show people that answer, they say things like, you cheated. You went outside the box. I didn't say there was a box. Right? So, this is an insight problem because the way people naturally, spontaneously formulate the problem frustrates their attempts to solve it. People naturally, spontaneously, because you've all done connect the dots, you've got this assumption that you're only allowed to change direction at one of the dots. If you do a connect the dots and you start changing direction where there's no dots, you don't get a picture, you get some mess, right? People also naturally, spontaneously assume that they have to stay within the 9 dots. Yeah? So they sort of mentally put a box around this thing. And those are two natural, spontaneous assumptions that will make it completely impossible to solve this problem. So to solve it, what you have to do is break out of those assumptions and reformulate the problem as a different type of problem than the one you thought it was. So people tried all kinds of things to help people solve this. For example, the phrase "think outside the box" came from people trying to facilitate solutions of the 9-dot problem. By the way, it helps 0% to tell people to think outside the box, even when the problem is literally to go outside the box. It helps not at all to tell people that, which is funny because they do it all the time. What actually helps is drawing a larger box around the thing. So if you just give people the 9 dots within a bigger box, they're sort of people's attention is naturally drawn outside of the 9 dots. They feel like they're allowed to go outside the box. This facilitates solutions to the problem. Yeah? Okay. So this is supposed to be an example of an insight problem. A problem for which, I mean, you've got natural, transparent assumptions. Assumptions you don't even notice that you have about what would count as a solution to the problem and what things you're allowed to do to get to that solution. So you assume that a solution to the problem has to stay within the 9 dots. That's what your assumption about what the goal state is. And you assume that you're only allowed to change direction at one of the dots. It's an assumption about what you're allowed to do to solve the problem. Yeah? And so in insight problem solving, which, like, this is not like coming up with a theory of relativity, right? This is a fairly straightforward problem, but nonetheless, it still requires you to do this framing, breaking out of a frame, and then reframing the situation. So I'd suggest to you that many of the problems that we face are like this. So it's not just science that has this issue of transparent assumptions, assumptions that we see right through and can get trapped by. Yeah, so in some sense, the more training you have in a paradigm, the less you see the paradigm. The less you see it as substantial assumptions, and the more you see through it as just the way that it's done. Yeah? Let me do one more example. So here's what's called the mutilated chessboard problem. Here's one more insight problem, because I think these are fun. All right, so so this is a chessboard. It's got, it's 8 by 8. And imagine what we're trying to do here. So imagine trying to cover this thing with tiles, right? And one tile is exactly 2 squares large. Exactly 2 squares large. Okay. Now, if there was no missing corners, how many tiles would it take? 64 squares. Each domino covers 2 squares. This isn't the problem yet. This is the easy part. 32. It takes 32 to cover. If it's 64, it takes 32 dominoes to cover it completely without any overhang or overlap, right? Okay. So now the question is, can you, with 31 dominoes, suppose you knock out opposite corners, with 31 dominoes, can you cover this board completely with no overhang or overlap? And prove your answer. Don't just say yes or no. Prove to me. I promise this is possible, but probably not in the way that you're thinking. This is it. It's an insight problem. So I can tell you straight off, your assumptions are frustrating your attempts to solve this thing. Okay. I won't torture you quite as long with this one. So people naturally treat this as what you might call a tiling problem. So probably what you started, if you're like most people, what you started to do was mentally go, there's one here, there's one here, there's one here. Okay, I got to turn. Okay, I'll put one here, put one here. So you just started trying out the ways of tiling dominoes on this thing. Yeah? You're not supposed to fold the board. It's supposed to be flat.
Okay, I was going to say if we're supposed to fold the board, I'm going to get mad.
No. You leave the board just the way it is. Okay. So the number of possible ways of tiling is astronomical. One particularly keen math student filled like 10 Hilroy notebooks trying to exhaustively search the space of possible tilings. I'll tell you that's not how you come up with a solution to this thing. I've given you one of the hardest versions of this problem because the thing I've given you here doesn't have black and white. So a chessboard, a normal chessboard, has white, black, black. And this corner would be black, and this corner would be black. Now notice that any given domino has to cover both a black and a white. Yeah? Any given domino covers a black square and a white square. You've removed one black square here, one black square here. So can you cover it completely with exactly 31 dominoes? No. Because any domino has to cover one black and one white. You've removed two black squares. Therefore, there's no way of putting dominoes on this that you get 31 that you're each covering a black and a white, right? Because you've removed two black ones. There's more white squares than black squares. Each domino has to cover an equal number of black squares and white squares. Therefore, you cannot cover this exactly with 31 dominoes. Ta-da!
Could you give us that one first so that we would like reframe to think that we would be able to do this and make that sound?
I don't know. No, I thought I was doing them in ascending order of difficulty. That was it. Okay, so the way that people naturally, spontaneously approach this problem, they're never going to solve it. Yeah, there's just too many ways of tiling this. So as a tiling problem, it's insoluble. But as a parity problem, so there has to be an equal number, each domino covers an equal number of black and white squares. You've knocked out two black squares, therefore there's no way to have just exactly 31 dominoes covering all of these squares.
A computer programmer would be able to solve it. They would write a piece of software that would calculate every possibility.
Maybe, unless the number of possibilities is astronomical.
Is it? Like, how do we know how many possibilities?
I don't off the top of my head. No.
Okay.
Yeah. But there's a much easier solution, right?
Yes.
Vastly easier. And again, it's one question is the time energy spent versus the result that you're getting. So, insight problems. And insight problems in general, there's a whole bunch of these things. There's a bunch of cheesy ones. So here's one that they do in the psych literature. A man marries 20 women a week, and yet he breaks no laws, and it's illegal to be married to more than one person at a time. How is this possible?
Divorce?
No, so he never gets divorced. He's the priest. Yeah, exactly.
Murder?
No, he's the priest.
No, you could solve, like, he's marrying the woman and then
No,
marrying.
murder is against the law. I'm happy to infer. No, he breaks no laws and he divorces nobody. Sorry, I left out that he divorces nobody.
Okay.
He's the priest. He marries 20 women a week in the sense he gets them married. This is like a bad pun. Okay, all right. Anyway, there's a whole bunch of these things, a whole bunch of insight problems. There's a rich psych literature on what helps or doesn't help people solve these things. But I just want to give you these as a kind of example to show you that the stuff I'm talking about, paradigms, and the stuff about the problem of noticing is not science exclusive. So I'm not saying like, science, you've got this weird problem that nobody else has. Everybody has this problem. Everybody has this issue of making assumptions about the kind of problem that you're facing and the relevant strategies for solving it. And those assumptions sometimes work great. Again, if you're trying to multiply a couple numbers together, you got all of the assumptions right. I mean, you got to university, you passed all of your high school math classes, you know how to, you know what the relevant operators are for simple arithmetic and stuff like that. Most of the time, you know what the relevant operators are. But a lot of the time, a non-trivial amount of the time, you have to do some reframing. That is breaking out of the assumptions that you literally, I mean, and I think it's actually literally perceptual that you see through them. So, I mean, your assumptions are like your glass, like almost all the time I see through my glasses, right? I don't see my glasses. They enhance my vision because I don't see them. Those are like the assumptions that you bring to bear in the world almost all the time. They enhance your problem-solving ability because you don't see them. But once in a while, I have to take them off to get them cleaned, right? So I have to like fix up the lenses through which I see the world. And that's when you sort of have to break out of your assumptions, maybe change them a little bit, and then re-enter them in an improved way. So just to make it sound like I just want to make it clear that I'm not picking on science or scientists when I'm talking about this stuff, yeah? Now, talking about framing and reframing and the way that your research program can present some aspects of the world to you as relevant and exclude others as irrelevant. Grinnell has a really nice example from his own research. So remember last time we talked about how he made this switch from studying the effect of citric acid on rat liver cells to cell adhesion. And the cell adhesion thing was like a big part of his career. So studying cell adhesion turned out to be a really good move for him. So when he starts studying cell adhesion, what he's interested in is the number of cells that stick to a petri dish, because that's the kind of framework in which he originally encountered this problem. So he's making graphs like this, like given some treatment and given some amount of time, how many cells stick to the petri dish. Perfectly sensible way of going about this. He's taking photographs, but they're not very well done. They're not part of his research, so they're not presented in the journal articles. For him, the data is just how many cells stick. Now he's getting information about the shape of the cells, but that's not data for him right now. That's not interesting, it's not important. He doesn't report it, he doesn't take care to kind of accurately capture it. But as his sort of practice with this develops, so he starts collaborating with people who are really good at microscopic photography, and he starts teaching. He says he teaches a first-year class on histology, where the shape of cells is one of the important things that they talk about in the class. He starts realizing that actually the shape that the cells take is more diagnostic for the kind of things that he's trying to study than the number of cells that stick to the plate. So he makes this shift where the thing that was data before is no longer part of what he's talking about. So it becomes, in some sense, noise. And the thing that was noise before, which is the shape, overall shape of the cells, becomes the data that he's interested in. So now his journal articles are filled with these pictures of cell shape, and that's diagnostic for him of whether he's getting good cell adhesion or not. So this kind of shift from what counts as data happens. You know, this is a more sort of micro level than a massive paradigm shift, but this example nicely shows how it happens all the time within scientific practice, where something that used to be irrelevant becomes relevant, something that used to be relevant becomes irrelevant. Yeah? As you take different things to be, and this is like you can think of it as like a micro paradigm shift. Thomas Kuhn talks about paradigms in this very large sense, like behaviorism and Newtonian mechanics. But he also talks about like little paradigms within paradigms. So here's a little micro paradigm shift from studying cell adhesion in terms of the number of cells that stick to studying cell adhesion in terms of the shape of the cells. Yeah? So again, things come into focus or go out of focus. Things become data or stop being data depending on the theoretical framework that you're bringing to bear on their research problem. So this is the problem of noticing. It's not really, I mean, he's reporting his successes at coping with the problem of noticing, that what you notice, what's important to notice, shifts over time. Yeah? Okay. He gives this wonderful little anecdote. In 1913, archaeologist Hans Reck discovered the first human skeleton in Olduvia. I'm almost certain I said that wrong, in Africa. He also reported, surprisingly, that there were no stone tools in the area. Weird to find human remains with no stone tools. Years later, Reck returned with fellow archaeologist Louis Leakey. This was before Leakey's first visit to Olduvia. Oh man, Olduvai? I'm definitely saying that wrong. Olduvai. Okay, thank you. Okay, before leaving, Leakey bet Rec that they would find stone tools within 24 hours of arrival. Leakey won. Olduvai Gorge contained thousands of tools. Different rocks were available for making tools in Europe and East Africa. Rec had been looking for European-style Stone Age tools. On his previous trip to Olduvai, he had seen the rocks but did not notice them as tools. Yeah? So this is getting right down to a perceptual level. He's looking at the ground saying, do I see any stone tools? And coming up with the surprising answer, no, because he doesn't know what to look for. He literally fails to notice the data because he's got a specific framework about what counts as an instance of stone tool that he developed, quite honestly in researching in another area, but which utterly failed him to transport to a new research problem. Yeah? So a really nice, literal, perceptual version of the problem of noticing. I quite like that one. Okay. All right. So let's do a little shift here. So when we're talking about noticing, when we're talking about what's relevant or irrelevant, we're talking about framing problems as kind of cognitive issue. Let's talk a little bit about how what you might call ideology plays into this. So now we're talking not just about what does a stone tool look like, but the broader social, political value structure in which people are embedded. This guy, I don't know if you might be too young to remember Donald Rumsfeld. In the run-up to the Second American and Iraq War, Rumsfeld said the following. The idea was that Iraq had a secret cache of weapons of mass destruction which would justify the invasion of their country. So there are known knowns. There are things that we know that we know. There are known unknowns. That is to say, there are things that we now know we don't know. But there are also unknown unknowns. Things that we do not know, we don't know. That was the last one was supposed to be the scary one, right? That's supposed to be like, maybe they got nukes and we don't know that they have nukes. Okay, so this is a nice sort of epistemic classification scheme, but there's a missing one, isn't there? Yeah.
Can you justify anything with that?
Well, probably. Well, I mean, he's not wrong, is he? I mean, the fact of the matter is that there are these categories of things. There are things that you know. So, for example, I know that the lights are on, and I know that I know the lights are on. There are things that I know that I don't know. I don't currently know how many students are in this classroom. I haven't done a count. I know that I don't know that. And there are definitely things that I know that I don't know that I don't know. I can't give you an example, obviously. I mean, he's not wrong about this, right? Yeah. Unknown knowns. That's exactly right. So this guy, Slavoj Žižek, points out that there's a crucial missing element here. Unknown knowns. Things that you know that you don't know that you know. So these are the sort of transparent assumptions that you make about the world. Things that are so, I love the phrase, blindingly obvious. Things that are so obvious that you're not even aware of them as part of your knowledge structures. And I propose that that's a really good definition of what you might call ideology. Yeah? Things that are so obvious to you that you don't even consider them knowledge. If you consider something knowledge, then you can critique it. You can ask questions about it. You can interrogate it. You can ask about your evidence. If something is an unknown known, something that that's so part of your basic worldview that you're not even aware of it, then you can't critique it. And I would propose that ideology potentially has a radically distorting effect on science. So unknown knowns, there are parts of your paradigm can be unknown knowns. They can be ideological in the sense that you don't even think about questioning them. But stuff like, Newton's notion of absolute space, he was having actual debates with other people at the time about it. He was clearly aware of it as a substantial belief. Once we've cracked open the linear model of science. We've seen how the ways that you pay attention, the things that you find relevant or important or interesting, structure the way that science unfolds. It leaves open this kind of nasty, somewhat scary possibility that the political, social ideologies in which you're operating might have an important role on the scientific process. So this is something that I think we should be genuinely worried about. It's not the case that it's always distorting, but it has the potential to be genuinely distorting. So let me give you an example of, this is like the classic example of political ideology having a really bad effect on the scientific process. Like Sankoism. And just so I can keep track of, has anybody heard of this before? Okay, great. I love telling people new things, great. Okay, so I'm in the right line of work. Okay, so this guy, Sanko, was a Soviet agronomist. He studied agriculture, and he rejected what we call Mendelian genetics. So he had this theory of inheritance that went against sort of what we would consider how genes work. And this turns out to have, so I'm going to tell you this story as an example of ideology really distorting the scientific process. So just for let me do some background first. So before Darwin, there was Lamarck. Lamarck had his own view about how species change over time. Lamarck's idea was that acquired characteristics could be inherited. So why does a giraffe have a long neck? It's because it spends all day stretching, trying to reach the faraway leaves at the top of trees. And if you spend all day stretching, your neck gets a bit longer, and then your kids will have slightly longer necks, and they spend all day stretching, and their kids will spend all day stretching. And you sort of like, these characteristics that you acquire in your lifetime are passed on to the next generation. So if you spend all day in the gym, your kids will be buffer. If you spend all day at the library, your kids will be smarter. This is the kind of thing. Like, so the things that happen to you throughout your life, Lamarck thought, would have an effect on the next generation. So this is part of how he explained the change in species over time. Okay. So now this Lamarckian thing was considered by the Soviet Union in the 1920s. They were like, I don't know how much you know about the history of the Soviet Union. The 30s was bad times in the Soviet Union. It was not fun. A lot of people starved to death, and they were deeply worried about that. It's not like they weren't trying to keep people from starving to death, but they were anyway. They're pouring huge amounts of money into trying to make agriculture more scientific. At the time, in the 20s and 30s, they thought that they contrasted bourgeois and racist Lamarckism with the more properly Marxist Mendelian genetic theory. So Mendelian genetics is kind of what we have today. So you've got, the two parents, and then they produce an offspring, and that offspring will have some mix of the characteristics of the parents, but it's got nothing whatsoever to do with what's happened over the lifetime of the parents. It's just genes. So your genes you're born with your genes, you pass on your genes to the next generation. Your genes are not altered by what's happened to you over your lifetime. That's Mendelian genetics. Yeah. So they thought the reasoning at the time in the Soviet Union was that Lamarckism was kind of bourgeois and racist because it sort of put the onus on people for their characteristics of the people was a result of their individual actions. So if I go out and like try to improve myself, then my kids will be improved, and that's why. So they're like, that's why rich people have better kids than poor people, because the rich people really pulled themselves up by their bootstraps or whatever. So this was the picture of, they're like, yes. So the Marxist worldview was that environmental conditions cause the properties of individuals rather than the individual's behavior. So Mendelianism, that's good Marxist stuff, and Lamarckism is bad and bourgeois. that is until kind of the 30s to the 40s when Lysenko comes on the scene. So Trofim Lysenko had the right kind of credentials in the Soviet Union. He was born very poor, so he's born into the peasant class and kind of rises through the ranks. And he was a proponent of this process called, okay, well, I don't know how much you know about grains. I didn't, until I read this, I don't know anything. I'm not a farmer, so I don't know anything about grains. But apparently there's some grains that can be planted in the spring and some that have to be planted the previous winter. So you got to get them in the ground, let them spend the winter in the ground, and then they crop. So there's winter grains and spring grains. And farmers for a number of generations were familiar with this idea of vernalization, where you treat some winter grains that would have otherwise had to be planted much earlier with cold and moisture, and that makes them able to be planted in the spring. Okay, so you're doing this treatment on the grains to turn winter grains into spring grains. So this works, this is a real thing. Lysenko claimed, based not apparently on anything, that you could do this over and over again and that the effect would compound. So it's a kind of acquired characteristics being inherited. So if you keep doing this vernalization process, it would increase the degree to which your crop yields would increase. Your crop yields would continue to increase. So this, and he rejected the Mendelian genetic picture, right? So this is precisely acquired characteristics being inherited. And for one reason or another, the Soviet Union didn't really stick with things very well. They had a very complex, ongoing, developing ideology, but they decided that this fit better with Marxism because in the Marxist picture of human nature, the idea was that the environment shapes us much more than our intrinsic characteristics. So the kind of capitalist picture was, people who are, the American dream. If you've got the stuff, you're gonna succeed. And it doesn't matter whether you start at the bottom, you're gonna end up where you belong in society. And all society has to do is just make that vaguely possible, and your intrinsic goodness or badness would express itself. So it's all on you. You, the individual, are the explanation for where you end up in society. That contrasts with the way Marxists thought of things, which is that the structure of society is what determines the properties of individuals. So the class struggle is what makes people the way they are. So, trying to stay in the bourgeois class makes people bourgeois, and being in the working class makes people working class. The conflict between them kind of determines the characteristics of both. So it's much more environmentally focused. So your place in society determines what your properties are, rather than your properties determining your place in society. So this vernalization thing had a much more environmentally explanatory bent to it, right? It's not just the intrinsic properties of the grains, it's the environment that you put them in. An environment determines what kind of grains are going to grow. So they decided in the Soviet Union that this was the way things were going to be. It fit better with Marxist ideology, therefore it's the truth. And by 1948 or so, it became effectively illegal to disagree with Lysenko. So he rose right to the top of the ranks in the sort of Soviet agricultural science. And I mean, in the Soviet Union, illegal is illegal. Like, you do not mess with these guys in terms of, you don't pipe up and sort of say your own thoughts in this context. They will ship you to a very nasty place and they will send you to the literal gulags if you disagree with the party line.
It's like how bad professors get sent to the Durham campus.
That's not true at all. They're very nice over there. They're very smart and nice. All right. Okay. Oh, jeez.
I know things that
That's brutal. All right. Okay, so is it? Oh, okay, I'm not even touching that one. All right, we're not going to go there. Okay. So this goes down as one of the classic examples of they've got this social political value structure, and it becomes, I mean, the society is so rigid and so closed that anything that deviates from it is treated as a kind of crime. And Sankoism is taken up as scientific fact in this context because it fits Marxist ideology, not because there's any evidence for it. Like, the evidence is irrelevant. It turns out he doesn't really improve crop yields particularly. The old farmer's trick of vernalization totally works. It's the Lysenkoism thing doesn't work. So this is one of these really classic examples of ideology driving science and it having a really bad effect on the scientific process. One of the lessons that philosophers of science draw from this is that to do science properly, you need at least a minimally open society. Like, you can't do science properly in a completely authoritarian society where disagreement is a crime. Because what happens is this, right? Disagreement with the kind of ideology of the ruling classes, even in a scientific context, becomes a crime. And then you just get junk science, basically. You just get people sycophantically agreeing with whatever the people on top say. And that leaves out the kind of intercritical, like the way that science is supposed to work is you have an idea and I have an idea and we criticize each other's ideas. And in an authoritarian society, you really can't do that. So one lesson here might be that you need a certain type of society, maybe not a certain type of society, but you need for it to not be Soviet Russia in order to have a good scientific sort of like community going, yeah? Because scientific communities thrive on disagreement, open, honest disagreement, rather than sort of like they will literally send you to the gulag if you disagree. Okay, so to flip this a little bit, I mean, Lysenko turned out to be mostly wrong. Actually, it turns out that organisms can inherit acquired characteristics. There's a whole bunch of really interesting research coming out now about what's called epigenetics. So on your genome, on your DNA, there's a whole bunch of methyl groups. So there's these little methyl groups that like latch on to the outside of the DNA that act as a kind of punctuation to tell the transcription factors when to start transcribing and when to stop. And those things are both inherited and can be altered across your lifetime. So these are acquired characteristics that can be inherited. Similarly, the degree to which your DNA is this like big tangle, and the more densely tangled up it is, the less a part of the DNA is transcribed. So there's sort of like you can uncurl the DNA more or less to have different parts of it transcribed more or less, and that seems to be similarly both acquired and inherited. So it's not even that he was just completely wrong about the inheritance of acquired characteristics, is that it wouldn't have mattered one way or the other if he was right or wrong, because ideology was driving the process. Ideology was completely driving the process. Okay. So let me shift a little and talk about, I don't know, just... So while we're on the topic of ideology and science, let's talk a little bit about the ways in which, again, this is a story about the interaction between ideology and science. This is going to be a story about how science can be perceived, something can be perceived to be a scientific fact when it is in fact an ideological fact. So it looks like an objective fact about the universe because the values of the people judging it are so transparent to them. Right, their value judgments are so obvious, they are ideological in the sense that we just discussed, that it makes something look like a scientific fact when it's in fact a value judgment. So let's talk a little bit about, okay, so we'll do this Darwinism thing. I take it that you are familiar with this notion of evolution by natural selection. There's common descent. So Darwin proposed that we all come from some universal common ancestor. And of course, natural selection is the main driver, or as a big driver, and the explanation for why animals fit their environments. You get evolution by natural selection if these three things are satisfied. There's variation of population, the variation is heritable, and heritable variations are linked to different rates of reproductive success. That's all you need. That's kind of all the theory says. Yeah? That's basically the theory. Now, when people read this, they almost immediately jumped to, from a descriptive claim, a claim about how populations change over time, to a normative claim, a claim about what's good or bad. That is, nature is a big, fierce competition, red in tooth and claw, and that eating the losers is a good thing, basically. That whoever is strongest should dominate the weakest because that's how nature intended it. And that if you win some competition, that's actually for the benefit of all. So like vicious competitiveness and ruthless sort of like attempts to dominate everybody around you are actually nature's way of making everybody better off. And that's a normative claim, it's a values claim. Darwin heard about this pretty fast and thought it was funny. He says, I received in a Manchester newspaper, a rather good squib, showing that I have proved, quote, might is right, and therefore that Napoleon is right, and every cheating tradesman is often right. So he immediately heard people interpreting him this way and thought it was kind of silly. Right? So he's not making any claims about what's good or right. He's certainly not saying that might makes right. All he's saying is those organisms that leave more offspring will tend to dominate, populations will be made up of those organisms that tend to leave more offspring. Yeah.
The thing that resolves it is competitive exclusion, where you have two different species that evolve and then they each specialize in consuming a different type of resource, and that way they're no longer competing against each other.
That's one thing that helps, yeah, yep. Okay, so social Darwinism is a term of abuse. Nobody ever called themselves a social Darwinist, but this very quickly gets interpreted as, so Darwin's theory, very quickly, this is the huge colonialist project, so Europe's kind of crashing around the world, wrecking things and taking everything they can lay their hands on, and this was sort of justified in Darwinian terms. Like, it's good and right that we're ransacking India right now because Darwin, that's the natural order. Take what you can and screw everybody else. And that's just really not in the theory. Yeah? There's nothing in Darwin's theory that says this is good or acceptable or reasonable. So what they're doing, we might call this the naturalistic fallacy. Naturalistic fallacy is when you assume that just because something's natural that it's good. So cyanide is a perfectly natural compound. That doesn't make it good for you. It doesn't make it good to do. Observe what wasps do. Wasps will lay their eggs in other animals and the eggs will slowly eat that animal from the inside, avoiding vital organs so that they stay alive longer. That's not good. That's horrifying. That doesn't mean that you should do that too. Yeah? Okay, so what the social Darwinists have done is commit the naturalistic fallacy. They've assumed that just because something is natural, that means it's good. And they've also done something, so that's a fairly simple just error in reasoning. They've also just read more into the theory than actually was there. So here's where it goes. Eugenics. So Francis Galton was Darwin's cousin, and he thought that the theory entailed that we needed to intervene to make people fitter because civilization let the unfit survive and reproduce. So here's a very weird line of reasoning that goes well beyond anything that's in Darwin's theory. So the rich are rich because they have good genes. The poor are poor because they have genes that dispose them to laziness, criminality, alcoholism, so forth. But the poor have more children than the rich. And if you remember what we just said about what fitness is, it's having more children. That means the poor people are fitter. So if we were actually just sticking with Darwinian theory, the argument should end, the line of reasoning should be derailed right here. If people have more children, according to Darwinian theory, that means they're fitter. Being rich has nothing to do with it. So what we've got here is intensely social values being interjected into the theory and distorting it, basically. Saying, look, we can tell, of course, that the rich are superior, which I equate with fitness. Because I'm Francis Galton, and that's what I think about the world. So the poor have more children than the rich. Again, according to Darwin, that makes the poor fitter. So the rich should be encouraged to have more kids, and the poor gently discouraged with, for example, forced sterilization and stuff like that. Yeah. So this was immediately, so Galton takes from Darwin's theory this kind of social program of, we should encourage the rich to have more children, and we should forcibly sterilize people who have been institutionalized for alcoholism or mental illness or imprisoned, that kind of thing. Yeah?
Did they believe that like the rich and poor were like different species or something?
Not different species, but they have different genes. So there's variation within a population, and that the variation, the sort of natural, so the social place that you have in the world tells you how good your genes are, and therefore this distortion where the poor are having more children than the rich clearly needs to be corrected by eugenic programs. And again, the error here, I mean, one, it's morally monstrous, but two, the error is thinking that this is a scientific fact. And so what's happened here is science and values have been seamlessly blended together, and the people who are doing this, for them, the values are so obvious, so transparent, that they can't separate the two anymore. Here's a different take on what Darwin's theory meant by one of the guys that invented it independently of Darwin's. Remember Alfred Russel Wallace? So here's what Wallace says about sort of how this stuff should play out in social groups. So groups which cooperate are more efficient than groups with in-group competition, Wallace said. Therefore, cooperation will spread and take over the world. Kind of group selection. So those groups that are better at cooperating, that work together better, will outcompete those groups that are ruthlessly selfish. So rather than might makes right, cooperation will take over the world. Inheritance interferes with within group selection and therefore should be abolished. So rather than sterilizing poor people, we should abolish inheritance. So nobody should be born rich. And the subjugation of women interferes with what's called sexual selection, so should also be abolished. So sexual selection is mate choice. At the time, the belief was that in most species, women and females are the ones that make the mate choice, and therefore forcing women to, so when you when your father forces you to marry somebody for social reasons, that's a distortion of a natural process that would improve the species and therefore should be abolished. So Wallace takes this radically kind of quasi-socialist lesson from Darwinism, which he also invented, by the way. So he knows this theory as best as anyone. He independently created the theory. And rather than, so we've got two very different kind of social visions coming out of Galton and Wallace. Galton thinks the poor need to be viciously suppressed and sterilized. Wallace thinks we need to end inheritance and liberate women. Both of those, I would propose, are interpretations of a kind of morally neutral scientific theory through social political lenses. And both of them are in some sense treating their values as though they are factual statements. Yeah, they're allowing their political social ideologies to blend into their scientific picture of the world and maybe going further than is justified descriptively. Something like that. Yeah? I don't think any particular vision of how society should be organized emerges from Darwinism, personally. I don't think either of those are sort of straightforward. I don't think either of these views are straightforward consequences of the theory of evolution by natural selection. I mean, competition is a real thing. Cooperation is a real thing. genes are a real thing, but not as real as we once thought they were. I mean, the relationship between genes and phenotypes is vastly less direct than anybody thought it was back then. So like the complexity of the relationship between a genome and a phenotype is way, way more than we ever believed, or than these guys believed. So this all seems to be reading too much. So there's too much ideology in this science, right? Treating these as scientific facts, either the eugenics stuff or Wallace's stuff, seems to be injecting ideology into the belief system, which might be better off left. So you might want to sort of, what we need to do is separate the two. So by the mid-20th century, Galton's vision was defining public policy. So by 1940s, sterilization laws have been passed by 30 American states, 3 Canadian provinces, a Swiss canton, Germany, Estonia, all the Scandinavian and most of the Eastern European countries, Cuba, Turkey, and Japan. We had a wee little World War about it, if you recall, where we decided that eugenics was bad. So that mostly stopped it, except in Alberta, where it kept going till the 70s. And also, Aboriginal women are still being pressured into sterilization in Canada today. So, yeah. And all of this is under the kind of, I mean, it remains a sort of cloaked in science. It's cloaked in the authority and authenticity of science, but it's steeped in ideology. That's the point I'm trying to make. So once again, we've got a failure to separate out, what bits can science give us as, in some sense, value neutral facts, and how are our values playing a role in constructing our picture of the world? No. Sorry, this is a grim one. All right. Okay. So if we're going to draw a moral to the story, it's perhaps this: if you can't make space in your head for the idea that values and ideology can play a role in science, that can influence the course of scientific process, and furthermore, you can't see how ideology might slip its way in and posing as scientific claims, so ideology can pose as a sort of objective scientific facts, then you're going to have pretty serious distortions in your scientific process. So the cure I propose is to admit that ideology is a real thing, that there are unknown knowns operating in everybody's life. Like, you don't get to not have an ideology as much as we might want to. The best that you can do is constantly try to dig up those unknown knowns, become aware of those things that you're seeing through rather than looking at, and just acknowledge the ways they're playing a role in your thinking. So the more of that stuff you can dig up, make conscious, the more you can see the role it's playing in your reasoning and criticize it. Now that's the ticket here. What we want is to make this stuff no longer invisible, make it visible, because then you can treat it critically rather than uncritically. You can look at your glasses rather than looking through them. And most of the time, that's more work than you want to do. Again, most of the problems you face are more like 7 times 7 than they are the 9 dot problem. But if we're not aware of the existence of this as a problem, then we're utterly stuck within ideology rather than having the capacity to critique it and be on guard against it. Yeah? So try to keep the scientific process from being distorted by this stuff. Yeah? Okay. Sorry, that was dark. That was a grim one. Okay. Okay. That's it for today. Next time we're going to talk about credibility.